Welcome everyone. During this lecture we'll introduce scalars and vectors, the graphical representation of a vector, the graphical representation of vector addition. We'll show how to obtain vector components, and we'll also introduce the analytical approach to vector addition. Let's begin with the definitions of a scalar and a vector. A scalar is any physical quantity that may be represented by a numerical magnitude only. As an example of a scalar quantity, if someone were to ask you how tall you are, you would respond with something like 5'10". You're specifying your height with a numerical magnitude only, therefore height is a scalar quantity. If you're trying to decide what to wear, all you need is the numerical quantity related to temperature. And therefore temperature is a scalar quantity. If you're trying to determine whether or not to buy a car, a used car for instance, the odometer reading is very important. And of course, the odometer reading measures distance. So if someone tells you that the car has 200,000 miles, that is enough information. That numerical magnitude enables you to determine whether or not you want to purchase the car. Let's now define a vector. A vector is a physical quantity that must be described by a numerical magnitude as well as a direction. And so, as you can see, a vector requires two descriptions, the numerical magnitude as well as the direction. So as an example of a vector quantity, if let's say you're lost somewhere and you want someone to find you, you need to identify your position. And in order to do that, you will specify how far away you are from a specific reference point, and you also need to identify the direction that the rescue crew must head out in order to find you. So position or location is considered to be a vector quantity. Here's another example. Let's say that a police officer wants to pursue an automobile that's maybe speeding. And so in order to do that, the officer will need to know the velocity or the speed as well as the direction that the car is traveling. And therefore velocity is a good example of a vector quantity. Later on we'll talk about something called force, but right now let's just rely on the fact that we know that when a hockey stick pushes a puck, that puck will take off in a certain direction, and in order to determine how far it will take off, we need to know how hard it was hit. And so force is considered to be a vector quantity, because in order to determine where the puck will go, We'll need to know how hard it was hit. That would be the numerical quantity related to force, as well as the direction in which it was hit. We will now introduce the graphical representation of a vector. As an example, let's represent a position of 10 miles in a direction of 30 degrees north of east. The first thing we have to do is to introduce a Cartesian coordinate system. So let's do that. Here it is. Of course, this is the x-axis, this is the y-axis. Let's now show the directions. The positive x-axis is considered to be the eastern direction. So this is east. The opposite side is west. Positive y is north. And the negative y is considered to be the southern direction. We now need to draw our vector, and the vector is 10 miles long. In order to draw it, we have to select a scale. And for our purpose, I'll select a scale of 1 block, let's say, equals 5 miles. And so if 1 block represents 5 miles, our vector, which is 10 miles long, will be 2 blocks in length. And a vector is represented by an arrow. So it'll be 2 blocks long, and the direction is 30 degrees north of east. How do we identify this angle? Well, we look at the reference angle, which is the eastern axis, which is the positive x, of course, and from there we have to rotate 30 degrees to the north. So starting with x, if we start our rotation, we'll stop at approximately right here, which is a 30-degree angle. Let's draw our vector. It'll be 2 blocks long, about this long, and the angle is 30 degrees. We need to give this vector a name. We'll use a capital letter such as A, and to signify that this arrow represents a vector, which is again a magnitude and a direction, we will put an arrow on top of this capital letter. Now, the textbook uses bold-face typeset. We will use an arrow instead. Last thing I want to show is the fact that this vector is 2 blocks in length. Okay, let's take a look at another example now. In this example, let's represent the vector, which we'll call B, and we'll specify it as 30 miles long, directed at an angle of 315 degrees. Once again, we'll introduce our Cartesian coordinate system. There it is. This is, of course, our y-axis, our x-axis. And where is 315 degrees located? Well, we always start with the positive x-axis, and we start to rotate counterclockwise until we reach 315 degrees. Can you tell which quadrant we'll end up in? Let's find out. We're starting here. If we rotate out to the y-axis, that's 90 degrees. To the negative x-axis, we're reaching 180. To the negative y-axis, that's 270. 45 more degrees, and we'll arrive at 315. So vector B is located in the 4th quadrant. Now, it needs to be 6 blocks long, right? We chose a scale of 1 block equals 5 miles, so 30 miles would need 6 blocks. And so let's draw our vector. approximately 6 blocks long, and I'm just being approximate right now. There it is. The angle, as we noted earlier, would be specified like this. This is a 315-degree angle. The name of the vector is B, and vectors always have this arrow on top of them. And that's how vector B would be represented. These vectors can be represented in something called polar form. Let me show you what the polar form of a vector looks like. Vector A, if you recall, was 10 miles long and the direction was 30 degrees. In polar form, we would represent it like this. We would specify the magnitude, which is 10. We would draw something called an angle bracket, which is what I've just drawn. And inside the angle bracket, we will introduce the angle itself, which is 30 degrees. Finally, the unit is specified at the end. Likewise, vector B was designated as 30 miles long at a direction of 315 degrees. And this is how we would represent vector B. We will now talk about vector addition. In this example, we're going to introduce two vectors. We'll let the first vector, called A, equal 50 miles at a direction of 30 degrees. And vector B will be defined as a 25-mile vector directed at a 75-degree angle. Let's now discuss how to add these vectors graphically. So this is the graphical addition method. And it involves 3 steps. So, in order to add vectors A and B graphically, the first step is to draw the first vector with its tail at the origin. Of a Cartesian coordinate system. So we'll introduce our Cartesian coordinate system once again. There it is. And now we'll draw the first vector, which is vector A. Now, vector A is 50 miles long, and if we use a scale of, say, 1 block equals 10 miles, then vector A will look something like this. There's our 30-degree angle, there's vector A, and of course vector A is represented by 50 miles at an angle of 30 degrees. Let's move to step 2 now. Step 2 requires that we draw the tail of the second vector starting at the tip of the first vector. So let's copy our first diagram. There it is. And now we will follow the instructions. Now, in order to draw vector B, I will now create a portable Cartesian coordinate system, a miniature Cartesian coordinate system, and now I will draw vector B. Now, vector B is specified as 25 miles, so it's half as long as A, and it heads off in a 75-degree direction. So 75 degrees is roughly this angle that I'm drawing, and I'm trying to draw a vector that's about half as long as vector A. So there's our vector B. And we'll also note that this is our 75-degree angle. Let's now move on to step 3. In step 3, we must draw a third vector, which is called the resultant. Starting at the origin, and ending at the tip of the last vector. Which in this case, of course, is vector B. This vector represents the vector sum of A and B. So I've repeated our drawing, and now I'm going to draw the resultant vector, and again the instructions tell us to connect the origin to the tip of the last vector. So I'm going to connect those two dots, and if I do that, I will identify the resultant vector. And there it is. This vector is called, again, the resultant. It's labeled as R, and it represents the vector sum of the two original vectors, A and B. So now this resultant vector raises the following questions. How do we determine the magnitude? In other words, how long is the vector R? And we're also interested in determining the angle that is related to vector R. So let's pose that question and then we'll answer it. Again, how do we determine the magnitude and direction of R? We can do it graphically, but we would like to also know how to do it analytically. I need some numerical results. Well, in order to answer this question, we have to introduce the topic of vector components. And for this example, let me introduce the vector A. So we'll draw a Cartesian coordinate system, looks like this. And we'll draw a representation of some arbitrary vector, we'll call it A. It turns out that this vector has what's called components. The components look like this. If we complete the triangle with two other vectors, one being horizontal and the other one being vertical, those represent the components of A. The horizontal component is called A sub x, and the vertical component is called A sub y, and of course angle theta represents the direction of vector A. So let's define these components. Again, A sub x is known as the x component of vector A, and A sub y is known as the y component of vector A. I also want to call your attention to the distinction between A with an arrow on top versus A without an arrow on top. So we know that A with an arrow on top indicates the vector. Whenever we see A without an arrow on top, that is the symbol for the vector's magnitude. So A without an arrow on top signifies the magnitude of vector A. Okay? So vector A with an arrow on top actually has two components. It has a magnitude and it has a direction, whereas A without the arrow is only referring to the magnitude of this vector. So how do we determine the components? In other words, if let's say you're headed out along this path and it's 50 miles long, and then on the second day you would like to head out horizontally and then vertically to reach the same destination, the question is, how much distance would you have to cover horizontally and how much distance would you have to cover vertically? To answer that question, we have to consider the following. In order to find A sub x and A sub y, we will use the following equations. It turns out that A sub x just equals A times the cosine of the angle, and A sub y will equal A times the sine of the angle. And remember, the letter A without the arrow just signifies the magnitude of vector A. There's one other relationship that we noted earlier in our trigonometry review, and that is A, by the way, A is the length of the hypotenuse of this triangle. Well, the Pythagorean theorem states that the hypotenuse will equal the square root of the sum of the squares of the shorter sides. Now, the shorter sides, of course, are AX and AY. I'd also like to note that AX is the adjacent side relative to this angle, and AY is the opposite side relative to that angle. So A just equals the square root of A sub x squared plus A sub y squared. And with the knowledge of these components, we're getting closer towards being able to determine the magnitude of the vector R. So now let's introduce the analytical approach to vector addition. We're going to let the vector A equals some arbitrary magnitude, and that magnitude will be referred to as A without the hat. Before, I gave you values like 10 and 50 and so forth. Right now, I'm giving no values. This is just some generic magnitude and a generic angle, which we'll call theta 1. We'll also let vector B equal another generic magnitude as well as a generic angle, theta 2. How do we find the vector sum of these two vectors? Well, we'll start by drawing the vector sum. So step one is to draw the vector sum. for A and B. So we want to add these two vectors together, and that procedure starts with the drawing of the vector sum. So let's introduce the Cartesian coordinate system. There it is. And now we'll draw vector A, just some arbitrary vector. Let's say that this is vector A, and maybe this vector represents B. This, of course, would be the angle associated with A, which we called theta sub 1. And if we draw a portable Cartesian coordinate system right here, this angle is theta sub 2. What I'd like to do now is to draw the components of A. If we were to draw out the components of A, they would look like this. This would be the vector AX, and this would be the vector A sub y. And I'll do the same for vector B. So this represents the x component of the vector B. We'll call it B sub x. And this vector represents the y component, which we'll call B sub y. Notice that I don't have hats on A sub x and A sub y, and that's because I'm just referring to the lengths of these vectors. Next, I'm going to draw the vector r. And as you recall, vector r is drawn by connecting the origin to the tip of the last vector. So let's connect those two dots, and this is the vector r. There is our vector r in blue. What I'd like to do now is to isolate vector r in its own diagram. So let's again repeat this Cartesian coordinate system, but only show vector r. So I've reproduced the Cartesian coordinate system. This, of course, is x and y. And now I'm going to reproduce the vector r. There it is. We also want to note that vector r has its own components, and we will draw the components like this. This is the x component of r, and this is the y component. Let's label them as r sub x and r sub y, and also this is the angle that's associated with our resultant vector. The question now is, what is the relationship between r sub x and the variables that we see in the original diagram? Well, we'll evaluate that in just a bit, but first, let's note the relationship that we can see within this triangle. Specifically, we can note that the length of this vector r through the Pythagorean theorem just equals the square root of r sub x squared plus r sub I squared. And so, if we can somehow determine the value of r sub x and r sub y, we can now determine the magnitude of r. Let's compare the two diagrams that we're looking at right now. Can you see the relationship between r sub x and the variables defined in this diagram? Well, if you look carefully, this length, r sub x, seems to equal the length of a sub x plus the length of b sub x, right? If we count out the number of squares for a sub x and add the number of squares for b sub x that we're traveling horizontally, that would add up to the length of r sub x. So that's our first observation. We can note from our diagrams that r sub x just equals a sub x plus b sub x. Now let's take a look at the y relationship. Here's r sub y, and I think you see a similar pattern. R sub y, as you can tell, just simply equals a sub y plus the length of b sub y. So again, r sub y just equals a sub y plus b sub y. And now that we've established the components of the vector r, we can find the length of the vector r. So now the only question remaining is, how do we determine the angle for theta, in other words theta sub r, which is the angle of the resultant vector r? Well, to find this angle, theta sub r, we must use the following procedure. Step 1. We're going to calculate, using our calculators, the following quantity. We're going to find the inverse tangent of the absolute value of r sub y divided by r sub x. So in other words, this is how we calculate r sub y and r sub x. And once we do that, and we have the magnitude, we'll then reuse them within this equation and disregard the signs, because we will strip the signs away through this absolute value feature. And when we do that, there will be a value that appears on our calculator screen which needs to be adjusted. This will not necessarily be the angle. Step 2 requires that we adjust the calculator value. According to the following table. So here's our table, and let's fill in the entries. The first column notes the quadrant in which r lies. Next, we'll indicate the sign of r sub x and r sub y. And the last column denotes theta sub r, which is the angle we're looking for. So the quadrants are 1, 2, 3, and 4. Now, if we're in the first quadrant, when we do our calculation, we'll find that rx equals positive and ry equals positive as well. In the second quadrant, the x component of r will be negative and y will be positive. In the third quadrant, both signs will be negative, and of course in the fourth quadrant, the sign of rx will be positive and the sign of ry will be negative. If r is in the first quadrant, it turns out that the theta sub r, the angle that we're looking for, just equals the calculator value. Whatever's on your calculator screen, that is the value of theta sub r. However, if we're in the second quadrant, that calculator value has to be adjusted according to 180 minus the calculator value. In the third quadrant, the adjustment equals 180 plus the calculator value. And finally, if the resultant is found to be in the fourth quadrant, the adjustment is 360 minus the calculator value. We will now introduce an example that demonstrates the application of this material. In this example, a hiker begins his journey toward a lake by traveling a distance of 75 meters toward the east. He then travels 150 meters in a direction of 40 degrees west of north. Finally, he travels 60 meters in a direction of 20 degrees south of west and arrives at the lake. We need to determine the total distance traveled by the hiker, as well as the magnitude and direction of the hiker's displacement. Let's begin by organizing all this information within a table. So here's our table, and the first column will be headed by the vector's name. The second column will designate the magnitude of the vector. We'll designate the angle in the third column, followed by the x component and y component. Now, let's examine the first leg of the journey. We're traveling 75 meters toward the east. Let's designate that first leg of the journey as vector A. The magnitude is 75 meters, and the direction is toward the east, and that corresponds to a 0-degree angle. So the angle is 0 degrees. The second leg of the journey, we're traveling 150 meters in a direction of 40 degrees west of north. We'll designate that leg as vector B. The magnitude is 150 meters. We're traveling 40 degrees west of north, and let's determine the appropriate angle for that displacement. So I'll introduce a Cartesian coordinate system. Here it is. And if we're traveling in a direction of 40 degrees west of north, that means we need to refer to the northern axis, which is the positive y-axis, and then rotate 40 degrees towards the west. So if you can imagine that, we start here and then rotate 40 degrees towards the west. That is the angle that we're interested in for the second leg of the journey. So this is where the 40 degrees would be located. Now, we always want to specify the angle with respect to the positive x-axis when we conduct our analysis. And so, can you tell what this angle would be? Well, let's find out. Starting at the positive x-axis, by the time we reach the y-axis, that's 90 degrees, plus an additional 40 means that the angle is 130 degrees. And we'll place that value into our table. In the last leg of the journey, we're traveling 60 meters. We'll call that vector C. The magnitude is 60, and now the direction is 20 degrees south of west. Now, the reference direction is west, which is right here, the negative x-axis, and we have to now rotate 20 degrees towards the south. So if we rotated another 20 degrees from west, we would arrive approximately here. So this is our third vector. This is our 20-degree angle. And now the question is, what is the large angle? We always want to specify our angles with respect to positive x. So this is the angle that we're interested in. And you can see from the positive x-axis to the negative x-axis amounts to 180 degrees. We're going to add 20 more, and so the total angle is 200 degrees. And that's the value that we'll enter into our table. Let's also label these two vectors. So the first one I drew right here is vector B, and the last vector that I drew is vector C. And I drew this just to indicate the angles that we're interested in. I'd also like to show the actual path that the hiker traveled along in order to get to the lake. Let's do that next. So here's our Cartesian coordinate system. This is, of course, north, south, west, and east. The first leg of the journey is a 75-meter travel along a 0-degree angle. We'll represent it like this. This is vector A. Next, we're traveling 150 meters at an angle of 130 degrees. So I'll draw a portable Cartesian coordinate system right at this location. And 130 degrees relative to the x-axis lands us into the second quadrant. And now we have to extend this 150 meters. And so this is vector B. And of course, this is the 130 degree angle within our table. Finally, the hiker's traveling 60 meters at a direction of 200 degrees. So let's draw that. First, let me just move this vector B over. Next, we'll draw a portable Cartesian coordinate system right here. 200 degrees, of course, is within the third quadrant. We're going to travel 60 meters. So the third leg of the journey looks approximately like this. And we'll call this vector C. The 200 degrees is this angle right here. Now, the second part of the problem asks us to determine the magnitude and direction of the hiker's displacement. Well, the displacement is just defined as the straight line distance between where we started and where we ended. We call that the resultant. And the resultant can be drawn by connecting the origin to the tip of the last vector. Here's our resultant, and we will determine how long it is as well as this angle when we pursue part B of the problem. But the first part asks us to determine the total distance traveled by the hiker, and that's not a very difficult thing to do. So again, part A wants us to find the total distance. Well, it turns out that in order to calculate the distance, we just need to add the magnitudes of each leg of the journey. So the total distance is just a matter of adding the 75, the 150, and the 60, right? If we traveled this path with an automobile, that's exactly what the odometer would be measuring. A 75-meter trek this way, 150 meters that way. Sorry, let's backtrack. 75 meters this way, 150 meters that way, plus an additional 60 meters. So let's add these three values up. And if we add these, we end up with 285 meters for the total distance. In part B, we want to find the magnitude and direction of the overall displacement, which we call R. The first step is to determine the x and y components of the three legs of our journey. So in the first step, we'll determine the x and y components. Let's start with vector A. In order to find AX and AY, you can look at the notes that we developed earlier, and you'll find an equation that states A sub x just equals A times the cosine of theta, and A sub y equals A times the sine of theta. A refers to the magnitude of the vector A. Let's look that up in the chart. As you can see, the magnitude of vector A is 75 and the angle is 0. So this becomes 75 times the cosine of 0, and A sub y equals 75 times the sine of 0. Now let's enter these values into the calculator, and what we'll find is the cosine of 0 is 1, and so A sub x just equals 75, and A sub y will equal 0 because the sine of 0 equals 0. In other words, the vector A has no y component. Let's calculate B sub x and B sub y now. Just like we did for A, B sub x will just equal B times the cosine of theta, and B sub y equals B times the sine of theta. In this case, the vector B has a magnitude of 150 and the angle is 130. And B sub y will equal 150 times the sine of 130. Let's calculate these values using our calculators. So B sub x equals negative 96.42 and B sub y equals 114.9. Finally, we'll conduct the same calculations for Cx and Cy. So again, Cx just equals C times cosine of theta, Cy equals C times the sine of theta. The values for the vector C are 60 and the angle is 200. So this is 60 times the cosine of 200, and Cy equals 60 times the sine of 200. And let's carry out this calculation using our calculator. And the results are Cx just equals negative 56.38 and Cy equals negative 20.52. Let's now enter all of these components back into our table. Alright, so the value for A sub x, which of course is going to be entered within the x component column, is 75, and the y component is 0. For B sub x, we calculated negative 96.42, and the y component was 114.9. And finally, for C, we calculated negative 56.38, and the y component was negative 20.52. What we'll do next is calculate Rx and Ry and enter those values right here. And the way to calculate Rx and Ry, if you recall, is to just add these values vertically. In other words, Rx earlier was defined as A sub x plus B sub x, and in this case we'll also add C sub x because we have a third vector. And Ry is defined as A sub y plus B sub y plus C sub y. So let's enter these values into our calculator and then document the result. Okay, I'm calculating negative 77.8 for Rx, and let me just define this as R sub x. So again, R sub x equals negative 77.8, and for R sub y, I'm calculating 94.38. And so with these two values, we can now calculate the magnitude of the overall displacement as well as the angle related to the overall displacement. So let's do that next. Okay, so in order to calculate the magnitude of R, we will use this equation that we established earlier. R just equals the square root of r sub x squared plus r sub y squared. Let's enter the values that we just calculated. Again, r sub x was negative 77.8, and we have to wrap that with parentheses before we square it within our calculator, or you can just ignore the negative sign and just square the 77.8. Either way, you'll get the same result because squaring a negative eliminates the negative. Plus, r sub y we calculated to be 94.38. We'll square that as well, and our result equals 122.3. And of course, the units would be what we started with, which are meters. Let's now calculate the angle. So in order to calculate the angle, first of all, let's follow step 1, which is to calculate the inverse tangent of the absolute value of r sub y over r sub x. That results in the inverse tangent of r sub y is 94.38 and r sub x is negative 77.8, but the absolute value sign basically removes the negative sign. So I'll just enter it as a 77.8 and ignore the negative sign. I'll also wrap it in parentheses. Let's enter that calculation into the calculator. That results in an angle of 50.5 degrees, but now we have to adjust that angle through step 2. So in step 2, first of all, we have to note that r sub x, let's take a look at our table, r sub x had a negative sign next to it and r sub y was positive. So let's note that. Which means we are located, let's correct that, Rx is negative as we stated and Ry is positive, which means that we are located in the second quadrant. Let's now take a look at the table and see how to adjust the calculator value. Okay, so here's our table. R is located in quadrant number 2, and the adjustment requires that we subtract the calculator value from 180. So let's apply that to our problem. Alright, so theta sub r just equals 180 minus the calculator value. That's 180 minus the 50.5 degrees. And finally, the angle equals 129.5 degrees. So finally, we can specify the overall displacement as r equals magnitude and an angle, and specifically for our case, r equals 122.3 at an angle of 129.5 degrees, and of course the units are meters. And that concludes